Quadratic programming is a special type of mathematical optimization problem. It is the problem of optimizing a quadratic function of several variables subject to linear constraints on these variables. Problem formulation. The quadratic programming problem with n variables and m constraints can be formulated as follows. Given a real-valued n-dimensional vector C, an n times n-dimensional real symmetric matrix Q, an m times n-dimensional real matrix A, and an m-dimensional real vector B. The objective of quadratic programming is to find an n-dimensional vector x, that where xt denotes the vector transpose of. The notation xb means that every entry of the vector x is less than or equal to the corresponding entry of the vector b. A related programming problem, quadratically constrained quadratic programming, can be posed by adding quadratic constraints on the variables. Solution methods. For general problems, a variety of methods are commonly used, including interior point, active set, augmented Lagrangian, conjugate gradient, gradient projection, extensions of the simplex algorithm. Convex quadratic programming is a special case of the more general field of convex optimization. Equality constraints quadratic programming is particularly simple when there are only equality constraints. Specifically, the problem is linear. By using Lagrange multipliers and seeking the extremum of the Lagrangian, it may be readily shown that the solution to the equality constraint problem is given by the linear system, whereas a set of Lagrange multipliers, which come out of the solution alongside. The easiest means of approaching this system is direct solution, which for small problems is very practical. For large problems, the system poses some unusual difficulties, most notably that problem is never positive definite, making it potentially very difficult to find a good numeric approach, and there are many approaches to choose from dependent on the problem. If the constraints don't couple the variables too tightly, a relatively simple attack is to change the variables so that constraints are unconditionally satisfied. For example, suppose, looking at the constraint equations, introduce a new variable defined by where has dimension of minus the number of constraints. Then an if is chosen so that the constraint equation will be always satisfied. Finding such entails finding the null space of, which is more or less simple depending on the structure of. Substituting into the quadratic form gives an unconstrained minimization problem, the solution of which is given by, under certain conditions on, the reduced matrix will be positive definite. It's possible to write a variation on the conjugate gradient method which avoids the explicit calculation of Lagrangian duality. The Lagrangian dual of a QP is also a QP. To see that, let us focus on the case where and Q is positive definite. We write the Lagrangian function as defining the dual function, defined as, we find an infimum of, using hence the dual function as hence the Lagrangian dual of the QP is maximize. Subject to. Besides the Lagrangian duality theory, there are other duality pairings. Complexity. For positive definite Q, the ellipsoid method solves the problem in polynomial time. If, on the other hand, Q is indefinite, then the problem is NP-hard. In fact, even if Q has only one negative eigenvalue, the problem is NP-hard. Solvers and scripting languages.